All right, let's talk about a technique that's kind of like a secret weapon for coding interviews. It's called prefix sums. Now, the idea itself is super simple, but its applications, they can make your code, well, incredibly fast. Okay, so to kit things off, let's look at a really simple problem. Imagine you get this array of numbers. Nothing fancy, right? Just a straightforward list of integers. This is exactly the kind of thing you'd probably see in an early round coding challenge. So let's say I ask you to find the sum of just a small piece of this array. Like the numbers from index 2 over to index 4. That's pretty easy, isn't it? You just loop through them, add them up. 4 plus 1 plus 5 gives you 10. Yeah, simple enough. Okay, but here's the twist. What if you have to do that not just once, but maybe 10,000 times for all sorts of different slices of the array? And here's the real kicker. Each answer has to be instant. No waiting around. Suddenly, that simple little loop where you add everything up each time, well, that's what we call the brute force way, and it's just way too slow. It doesn't scale. This is a perfect example of where a tiny bit of work up front, what we call pre-processing, can give you a huge performance boost later. So let's check out the smarter way. And that smarter way is the prefix sum. The best way to think about it is like a pre-calculated running total. What we're going to do is create a brand new array where each spot in it stores the cumulative sum of the original array, all the way from the beginning up to that point. This is where the magic happens. Seriously, once you have this running total figured out, the sum of any part of the original array is just one single subtraction. You're not looping anymore. You're just looking up two numbers and finding the difference. It's that quick. And this little formula right here, this is what makes it all tick. To get the sum from some index I to another index j, you just grab the pre-calculated sum all the way up to j, and then you subtract the pre-calculated sum that ends right before I. And boom, the difference you get, that's the sum of your slice. It is honestly that simple. Okay, so how do we actually build this powerful tool? It all comes down to a one-time setup step, that pre-processing I mentioned. We're going to put in a little bit of effort right now so that all our future calculations are basically instant. And the process is really straightforward. Just 4 simple steps. We'll make a new array. We usually make it one element longer. We'll stick a 0 at the very beginning, which makes handling the edges a lot easier. Then we just loop through our original numbers one time, just once. At each step, all we do is add the current number to our last running total. That's it. One single pass through the data. Let's actually see how this works. We start with our prefix sum array, and it's just got that starting 0 in it. Okay, now we look at the first number in our original array. It's a 3. So we add that to our last running total, which was 0, and we get our first real prefix sum, 3. All right, next up, we move to the next number in the original array, which is a 1. We take our previous prefix sum, that 3 we just calculated, and we add the 1 to it. Our new running total is now 4. And you can see the pattern, right? We just keep this going. The next number is 4. We add that to our last running total of 4, and our new prefix sum becomes 8. Every new value is just the sum we had before, plus the next number from the original array. And there it is, the finished product. We've gone through the original array just one time, and now we have our complete prefix sum array ready to go. This single one-time cost, which is what we call linear time, or O of n, is the key that unlocks all those instant answers we were talking about. Okay, so the setup is done, our tool is built. Now for the fun part, the payoff. Remember that whole problem about answering thousands of questions instantly? Let's see how our brand new array just completely changes the game. I mean, the difference is it's night and day. With the brute force method, you're stuck in a loop, adding up numbers for every single query. But with our prefix sum array, it's just one simple subtraction. We've just jumped from what's called O of n time per query to O of 1, or constant time. That means it doesn't matter if the range is 2 numbers or 2,000 numbers, the calculation is always just one single operation. And to really put that into perspective for you, if you have a decent-sized array and tens of thousands of queries, this isn't just a tiny optimization. It is a fundamental game changer. We're talking about a potential performance increase of 10,000 times, maybe even more. This is literally the difference between a solution that just times out and fails and one that finishes in a flash. But wait, there's more. The real power here goes way beyond just these simple range sums. You can actually combine this idea with other tools, like hash maps, to solve even trickier interview problems.
Like that classic one. Find the number of subarrays that sum up to a specific target number, k.
So to crack this one, we're still going to calculate a running prefix sum as we move through the array. But here's the really clever part. We're also going to use a hash map to keep track of every single prefix sum we've already seen and how many times we've seen it. This map, this is our secret weapon for finding those subarrays that add up to our target k. Okay, let's walk through this example from the table. Our target sum k is 3. We always start by putting a prefix sum of 0 into our map to handle subarrays that start at the very beginning. So scene map starts with 0, 1. First number is 1. Our running prefix is now 1. The need is prefix minus k. So 1 minus 3, which is -2. Is -2 in our map? Nope. So we just add our current prefix of 1 to the map. Next number is 2. Our prefix becomes 1 plus 2, which is 3. Now what do we need? 3 minus 3 is 0. Is 0 in our map? Yes, it is. That means we found a subarray that sums to 3. So we increment our count to 1, and we add our current prefix of 3 to the map. Moving on. Next number is 3. Our prefix becomes 3 plus 3, which is 6. What do we need? 6 minus 3 is 3. Is 3 in our map? Yes, it is. We just added it on the last step. So we found another subarray that sums to 3. We increment our count to 2. See how that works?
So this is the whole idea right here. If the sum up to our current spot minus the sum up to some older spot equals our target k, well, a little bit of algebra shows that's the same as saying the current sum minus k equals that old sum. So if we can instantly look up that prefix old value in our map, we've just proven that all the numbers between that old spot and our current spot have to add up to exactly k.
So let's just wrap this up. What we're doing here is a classic space-time trade-off. We're using a bit more memory, a little more space, to store our pre-calculated values. And what do we get in return? We get our answers in what's called O of 1 time. That just means it's super, super fast, and the time it takes doesn't change even if the array gets bigger. And for a whole lot of problems, that's a trade you'll want to make every single time. And you know what's cool? This whole idea doesn't just stop with simple one-dimensional arrays. You can extend the exact same principle of a running total to 2D grids or matrices. And that lets you calculate the sum of any rectangular area inside that grid, you guessed it, also in constant time after you do that initial setup. So this all brings us to one last thought. Prefix sums are really just one example of a much bigger, more powerful idea called pre-computation. It's this whole concept of investing a little bit of work up front to make everything you need to do later on massively faster. So the question I want to leave you with is, what other problems could be simplified by doing this, by pre-calculating a running value? Think about it. It applies to way more than just coding.